Hey, it's Brain Muffin back with the Braincast, episode 6. It's been a while since we had one, so we're going to talk about something today, a little bit nerdy and a little bit dirty. So up today, we have the concept of a linked list, and we're starting this a little bit differently. And so we're going to talk about the linked list a little bit and what it is and what it does, and we'll see some examples. We're going to show a C example, which you kind of see here in the intro, and we'll also do something in C sharp or F. Yeah, I don't think we're going to do it F sharp, but the concept is pretty interesting. And you might be thinking, well, and today with collections and all this other stuff, why in the world would we need to have a knowledge of linked lists? And it's so mundane and it's so primitive. Well, underneath many of those collections are linked lists. Now, what we won't be talking about are B trees and all that other stuff, which can use this concept in a more economic and efficient fashion, but it's still underneath. They are still linked lists, and so we'll look at a simple linked list, and another time we'll look at a double linked list. All right, okay, let's get started. All right, so let's very quickly review of what a linked list is, just in case someone's not 100% sure and what that's going. So I'm just going to use a little drawing program. Computer File has a very good video where they use Legos and stuff like that, but they taught for a long time about a linked list, but it's really simple. So let's say that this box just represents some kind of data structure. It holds something of value, some kind of data. We don't really care what for this point, but we want to link them together. We want one to kind of flow after the other, kind of put them in line, if you will, put them in the queue. So we have our data structures, maybe in here there's strings and integers, doesn't matter. And the idea is we attach a little bit of piece onto it, okay, so that it can in turn point to another instance of the same data structure. Now I know I'm just using boxes, but it's the same type, we'll say. It's not necessarily the same instance, obviously, of the data structure, and hopefully it isn't. So it has a pointer or has a reference, depending on the type of language. And so there is this idea that it can point to the next one in line. Now, if there isn't one, then it won't point to anything else. Now, obviously here, I'm going to run out of screen real estate, but the concept this actually kind of represents is still valid because they could be anywhere in memory. The next one, it doesn't even really have to be sequential. It just points to the next one, which then in turn points to the next one. And then eventually what we have at the end of it, this will point to nothing, and we'll be able to detect that. So that's essentially the very simple explanation of a linked list. So we have some data structure that we have. Now, I know these are all drawn different sizes. That's just because I'm not an artist. But depending on the type of data, they could take up different amounts of memory internally. But that's a topic for a bit more in-depth discussion. But basically, we have an item here. It points to the next item. So like, let's say that we have data 1, okay, and I'm going to place it. So it has something here, and then this next one gets created, and we have data 2 or whatever, and it has its thing, and then this one is data 3, data whatever, and so just to show that it has data. So and then this one also points to nothing. So let's look at some C code to understand how in the world we're going to do this, and we'll do this is a simple linked list. This is a single linked list, and it goes one direction. All right, let's look at some code. So we're in our text-based editor. We're going to be using GCC here, and we're kind of using a mix of old C and new C, but no big deal. The idea here being the concept itself. So we are in C, and in C we have this idea called a structure, and we're going to skip just down the line. So we have struct, and we're going to call it a list item as one of our pieces. And let's say we were going to make the value. Now the value, this could be any size. I mean, I'm just going to have one line value here. I mean, I could just as easily say, hey, I got a name or whatever, but we're not going to worry about that. So we just have an integer value. And then as we showed in the diagram, we need to point to a type of itself. Now, the way that a pointer works in C is you put a star like that, so or an asterisk, to represent the where it's going to be held, and then we'll use an ampersand to get the address. This actually is a pointer in memory, so it points to the next location, wherever that may be. We don't really know, and we don't really care for this discussion, and that's really it. So we have a structure that we're going to define kind of globally here in this little simple file, and so it takes a value and it points to the next one. Now we're going to keep this fairly simple even in the coding side, And we're going to just create a main here, and we'll hardcode one, but we're actually going to need a couple of includes that I neglected to put at the start. And I keep forgetting that Vim is a little smarter than the old VI I learned 30 plus years ago. And I can move my arrows and stay in insert mode. We're just going to include both of these. We're gonna need both of them eventually. So let's just do this for the sake of brevity. And we're going to create a new one just off the bat. So in fact, what we'll do, and so we can struct list. And when we have a list, there's this concept of a head and a tail. So we're going to go ahead and call this head, and we're going to say right now it doesn't have any value whatsoever. And let's just hard code just to kind of get the idea of what we're doing. So we're going to say head equals, and we're going to new up the structure because head is a pointer. And now in old C, there is no new. So we actually have to do a memory allocation of what we want. And its memory allocation size is the size of the struct itself, which in this case is going to be a 32-bit integer and I believe a 64-bit address on this OS. This is Linux, and it is a 64-bit Linux, but I'm not 100% sure, and I haven't done some of this in a while. So we're going to just hard code this concept of a head, and then we're going to give the value a value. So we have this, and we'll say 100, and then we're going to do an output of it just to make sure that this works. And let's say current value %d, and then carriage return, and then head value. And so let me get my mouse pointer over here. So basically we have the definition of the structure. We're going to create one because remember, we don't have a new operator here. And so we have to do a memory allocation. That's what malloc is, the size of this item. And we're going to assign the thing to 100. And then we're going to print it out just to make sure that we have things going right. So call up the GNU compiler. Hopefully I did this right. And let's run it. Current value 100. So there you go. So that's just the top of the list. And so you're like, well, that's not very exciting, which it isn't. I will freely admit. And but let's say we want to input a series of these, and we're wondering how many there are and things like that. So and then we're just going to go down the list. So let's kind of tell, let's say this. Here's our rules. As long as you enter a number that's greater than 0, we're going to continue. And as soon as you enter a number that's less than 0, or let's say 0 or greater, we'll continue. And then as soon as you enter, say, a negative number, any negative number, we're going to spit out the list. Okay, so basically we have to keep track of the head and then where we currently are, so we can keep building the list, so we don't have to traverse the list every time that we add one. So so let's tell the viewer what we're going to do. And so we have this structure thing. We don't really care how many were entered, but we could maybe later. So I'm going to kind of cheat here and copy and paste some code so you don't have to watch me do so much. And I did forget we need to have a place for the number that they entered to be set. And I'm going to go ahead and spit all this code out. Because you don't need to see me type continuously and stammer. And as I well, what do I say next? I don't know. So actually I have this, this piece is pre-written, and I'm trying to copy and paste. They're using old DOS terminals here. Well, I shouldn't say DOS. This isn't DOS. This is actually Linux. So And we'll go through this a little bit more, a bit more clarity here so that people understand what we're doing. And it's indenting way too much. It's got a tab character that I got to get rid of. All right. Good grief. I keep hitting tab. All right. It just doesn't want to behave. But I wanted to line that up, but there we go. Finally, I got the right spot. So here's what we're going to do. We're going to enter a number 0 or, well, it says 0 or less, so which is what we explicitly say here. So we're going to loop. And so while the input is above what we expect, we're going to show, hey, give me a number. This is a nice way to scan. And then here's what we have to do to build the list. So we have, remember up here, we had head equals null. So it's the beginning. We don't have a list of anything. And then we're going to, so hey, if it doesn't equal null, in other words, we have something and we've been kind of going, we have this concept of the current node that we're dealing with. And actually, we're going to traverse the whole list. So we build a new one. The current node equals head. And then we go through until we find the end. So basically, we'll remember that picture that we had. We had that last one at the end. It was just a box, didn't have an arrow. So it essentially doesn't point to anything. And that's what we're looking for with, hey, while it doesn't equal null, let's just scan the whole thing. And we're keeping our variable head by itself so that when we come back through, we're not at the tail again. We're still at the head. Now we are traversing, which is fine. There are other concepts and things of how to keep where you are and things like that, but we're not going to worry about that at the moment. So then we do our malloc again, and we could put this in a function. Basically, we could pass it the value that we have and say, hey, make me a new one. And so we don't have to repeat this code, which we might do here in a moment. And then we assign the value, just kind of like what we did in the very first part of the version of the program. And we make sure that the next one is null, so it's not undefined what it's pointing to. And we mistakenly think it does point to something. This is very important in C. You have to be concerned about your nulls, and C++ as well to some extent. Otherwise, hey, this is our first time through. It's the first number entered. We're going to do the same kind of thing, but at the head, we don't have to traverse anything. And then we're going to print out what they gave us so that we make sure that we understood. And then once they've entered a number 0 or less, which breaks the while loop, we're going to say, hey, well, did they give us anything? And if they did, let's print it out. And again, the current node is at the top. Now, we don't necessarily have to do this. We could just use the head variable because we're going to be exiting. But for completeness sake and what we're looking for, now here's an interesting concept. We're going to do the variable. So this actually is a do while loop, which some languages do not have. So we don't have to do this twice. If we had to do a while loop, we would say, hey, okay, we're in here because we have something. We'll print it out, and while we still have more, print it out. Well, then we'd have to duplicate that code. This stuff right here, as opposed to say, hey, well, we got in here because we know we have something. So at least spit out the first one, and then while we have more, keep looping until we're done, and then spit out we're going to basically put all the numbers on a single line, or multiple lines if enough numbers get entered, and then we'll do a carriage return. Otherwise, we're going to say, hey, no numbers were entered, and we'll do a printf there. And this is really goofy that it's way over there, but okay. And we have to return. This is something from C. This is an old, because we said int at the top, we turn nothing. So let's exit out of here and recompile and run the program. So enter a list. So I remember I said, and it was, if I hit something, right, no numbers were entered. So that we know that case works. And so let's give it just one number, and then we'll do like -10 or something, and say the values of the list are 1. And then we can say enter a bunch of other numbers. Now these are integers. Now we're keeping things simple here. We're not looking to see if someone enters an incorrect value or a second value that we've already seen. It doesn't matter. Or string. This will make it an error if it's string. So there we go. So it spits it out pretty quickly. Hey, 10, and remember, it's going through that linked list of items and spitting out the value. And there we go. Now, as a consequence of the way that I coded this using this fscanf, what that does mean is that we can actually do this. We don't have to enter. Now, this is kind of weird. And even though it has a prompt, we can do this differently. So I'm going to try and do this really quickly. But let's say that we have a file of numbers. And I'm going to copy and paste some from another screen. And it's not, remember, it doesn't take a file name. But because of the way Unix and Linux work and this concept of putting things together and to build other things, we can basically pipe it in as input. And as you can see, we still get a prompt, number added, okay. We only get it once, but then the number added, these are the outputs that show up, and there it is. And so I could, come in here and enter any number of values. No, we don't want blank lines. Remember, whoops, we don't want strings. This thing is not really, as far as a program, is not completely robust to look for oddities like integers or not integers, text and blank lines and skip or whatever. But that's certainly left up as an exercise for the listener. But we can do this, and there's all those numbers again. As long as they fit into a 32-bit integer, we're good, which is a pretty big number. It is a signed number because we do care that it's signed. So it's like in the 3 billions or something. But I didn't enter anything that large. We also don't have any pretty output where we're looking to put commas and stuff like that in. Again, we could make it prettier because it's to get the concept of the linked list down. And so that the concept being that, hey, we have this data structure at the top, and we are, whoops, how did I get into a search mode? We have, but this could be any collection of information that we want to keep, any structure, and then we want to have a pointer to that same type. And then we just build the list and based on the input. Again, this part right here could be in a function, so that it would just say next node equals and then a call to that function, and we would pass the parameter of the value that we received, and then we would just basically have one line here and one line here. Really, it's the difference in what we're assigning. We could do a couple other shortcuts, things that would help us go, but again, we'll cover that in some other Braincast. So there we go. So that's nice. That is looking at it in kind of the old school way or a very primitive way using pointers. Well, great. What if we have a language that doesn't have pointers, and say Java or C# or something where we just have references? Can we still build a linked list? Well, remember we talked about it. It's a reference to something else. And here, in this case, the reference is using a pointer, but the reference could also just use suggestion of a thing. Well, I'll tell you what. Let's fire up Visual Studio and see if we can't do this in C# as well. All right, so I was gonna, do a kind of a code along like I did previously in C#, but I decided I've already done enough coding, people watching me code, and I thought that was kind of boring. So I'm like, let's do something a little bit different. So on the left here, hopefully everything can be seen very well, is the C code that we wrote, and with all the things. And we did say that this part and this part could be, we could put that in a function call and return, so we'd have like current node, next node equals, and then some function call, and put these 3 lines in there, and send some stuff as parameters. And we're going to make note of that and kind of use of that in this next thing. So this is a C# implementation, and why is it complaining about? No, just forget it. This is Visual Studio Community, and it likes to complain constantly. So over here, we've hidden some of basically the same basic premise is going on. In fact, some of the same, or very, very similar, I should say the same code. There's a very similar code that's in C# that we had in C. So on the left-hand side, we have C. On the right-hand side, we have the C# implementation. And now this is the main program where, hey, we're going to enter some stuff. So we initialize some variables. We print out the exact same message, building a list of positive numbers, blah, blah, blah. Enter a number. We're going to make sure, hey, you entered something. We're going to parse it. Now this will, if you enter a bunch of, non-numeric characters, this is going to blow up, but that's fine. This is just the idea is to get the idea across. Some people are going to forget it. If you did something, so we're going to parse it into a number because it comes in as a string. This console.readline reads a string only, but it's the same thing as we're doing fscanf here. Where this says, hey, do a decimal. And that's what we provide the address of the thing, and it puts it in there. This is kind of a pointer too as well. which is what this method takes. It's actually, forget it. So, and then we have this odd thing where we're saying head equals list item dot add node, the number entered and the head. So head, obviously, when we first start is nothing, right? Just like we did over here, we put the head equal and null. Remember, we're using references and not actual pointers. So this is kind of weird. Well, wait a minute, we're passing head, but because this code here, we've hidden inside this static. This is a static, and we'll get to it in a moment. And then we at the bottom say, hey, if we had something, let's iterate it. Now here we also have a little bit different concept. Instead of looping through like we did over here, and we went through all the linked list, we have that concept, but we're getting an iterator from this numerator, iterator numerator. It's like anyway, and saying, hey, while we have something still to show. So the move next has to happen first as opposed to the do while like we did previously. Spit it out. So current is going to have integers. So as you can see from the pop-up here, we say, hey, we have an enumerator of integer because we're just going to spit out the integers that we entered. And then we're going to write line. And if we don't do anything, we're going to do no numbers entered. Similar to over here, the list is empty. I guess I could add that. Hey, let's go ahead and add that. We don't need the new line because this already does that for us. This print line prints an actual, and it knows based on the system you're on what new line character looks like. And like in DOS, this needs to be /n/r. And so it knows. And then remember, this is .NET Core. So this is running on a Mac. It's not running on a Windows machine, but it is .NET. And there's all of the things. Now I'm going to go off screen here a little bit, and we're going to build it to make sure everything's okay. And just to show you, I'm going to run it before we show some of the innards. So here it is. And we're going to enter 10, and let's enter 20, and 100, whatever that number is. And then some randomish numbers, hopefully not too big. We may have blown up. We did. All right, sorry about that. Let's try that again. It's like I said, it's not robust, but I'm trying to get the idea of the linked list across, but obviously we'd have all kinds of safeguards if this was production code. But again, this is the idea. And see that we have leading 0, and -1 is good enough. So there we have we spit out the numbers, as you can see, and everything's good. But it's like, well, what? But all right, so fine. Let's look at this list item class. So I chose to do this more of an object-oriented way. This is actually with a little bit of change. You can make this immutable. We have the values read only, and you can even make this immutable if you wanted with a private constructor. So we have this public constructor, but we don't really use it. In fact, we can probably make it private and be done with it. There aren't any reasons not to do that because of the code changes. I actually made this a static, and so it can get to private constructors. So the idea here is encapsulation. This is something that is really lost in modern object-oriented programming and is probably worthy of a brain vlog item as opposed to the Braincast. So we have several concepts going on here. But let's just check on it. So similar to what we did in their structure, we had the value and we had a pointer to the next thing. We do have, and let's tighten this up so that it's easier to see. And in .NET, this underscore actually is meaningful as a local variable. This is kind of an annoyance to me, but this underline actually is meaningful. And so the idea here is we call this static, and what this means is this exists even when there isn't an instance of list item. You have to say list item.add node, and we have this new value and we pass the head. Now this code should look familiar. This is very, very similar to what we did over here, where we said, hey, but we don't have to do this malloc stuff and there was all this other nonsense. We're hiding that in a constructor. So we're saying, hey, if head equals null, so if they pass us the null, let's, or not equal to null rather, we got to iterate through the loop until we get to the end, just like we did here. And then we're going to say new. Remember in C, we didn't have a new. We had to do malloc. We're going to do a new. I think I'm way too loud. Let me double check my levels. Yeah, I'm way too loud. So we have a new, and that takes the place of these 4 lines of code. Actually, these 3 lines. But and we pass it the new value. And new value says, hey, I'm going to assign that. I'm going to create one. I'm going to assign it. The next node is null because we're only adding a single. And so we say, hey, our current node, remember, current node not equal null. So this will keep looping. And as soon as that's null, hey, we're done with the loop. We're at the end of the list. We're going to add a new item, and that's all we have to do. That's very similar to what we did over here. We did a malloc, okay, of the next node right here. Created a new one. We said the current node equals that next node, and then so we had to skip to it. And then we had to assign the number and say, well, and it's the end of the list, so we're going to make this, instead of undefined, we're going to do a null. Exact same thing here. And then we return it. And otherwise, hey, we don't have anything, so we're going to create a new one. Exactly what we did here. Now we're going to return this because we're assigning it. And so that's what this one line does, all of this, essentially. And then we have the added, just like we had here. And we're good. And now, okay, so that creates the new one. But it's a reference. It's not a pointer, but it's a reference, but it is a linked list. And now we want to enumerate. So we want to go through the whole list. Well, we have this code here with this do while. Well, I just pushed it into enumerator. This is an enumerator block. It uses the enumerator interface, and we say we want an integer. So I've type integer, and we have get enumerator. So this is public. This is public. These can be seen. Now this is on a particular instance. This is instance free, but this has to be on an instance, so it goes through that particular instance. And we do, and our return is kind of buried in here. It's kind of a little bit hidden, but the concept of the yield is that it's only going to do this when it's needed. So let's say that for some reason, let's say this was a list of 1,000 items, and every, 40 rows, we were going to do some kind of page break or something. So in here, okay. Then while we were doing that page break nonsense, so basically what will happen is this will go up into that stuff, do the page break nonsense. In the meantime, this isn't being called. So this is what yield really helps. But we're doing a very, very similar thing, except we're not printing. We're just doing, hey, we're doing the same do while, right? While we actually have something, send the thing back that we want, which is the value, and go to the next item. Print out the thing back and go to the next item. Very, very similar code, exact same concept. Very, very similar code, right? The only thing that's different really is these are the two lines. This is instead of doing a print, we're doing a yield. Again, if this was in a function, we could do something like that. And we're doing this piece. So what yield, we don't have to do cross-cutting or anything nonsense, but this is very, very similar, except because we don't have a pointer, we don't have the arrow, we actually have a reference, we just have dot. That's it. And these are all internal. So the values are fully encapsulated as opposed to struct. Now C# does have a struct, which everything's public by nature, which is what's here. C doesn't have that concept, C++ does. So we encapsulated our state, right? We get the new state, we assign it, but the outside world is not privy to what's going on, and we give it, this is how it gets access to it. And that's exactly what we see here. We say, hey, let's get the enumerator. While we have something, spit it out. While we have something, spit it out. And that's it. And so now if we run it one more time, and I know we made a couple live changes, which is always dangerous, because you could always be wrong. I don't want to get too large. And let's do -1. And again, we see the exact same thing. All these numbers spit out just like that. So there we go. And I just should have hit enter and let it continue. So this is a bit different object-oriented approach than what we have in this procedural structured approach over here. And I know some people, we can make functions. And that's what the idea of a linked list. Remember, we want to point to the next thing. We have a reference to the next thing. Here, we have a reference to the next thing. We have a pointer to the next thing. And its concept is very interesting. Now, obviously, or perhaps not, but when we look at this iterator here, if we have a long list, this could be, it could take a long time to get to the end. And we actually could utilize an internal enumerator instead of this while loop, but it could take a long time to get to. Basically, it's on the big O is of order n to add something, right? However many n items we've added, we have to skip through all of those to get to the end. So there are some efficiency issues, but it is a very simple idea to linking data together in some fashion. Now this obviously we're just doing it the way we're getting it in. I mean, over here, remember we even did the cat where we read it in from a file and we spat it out in the exact same order. We didn't do any ordering. But it's a very simple but powerful concept that can be utilized in many different variations to produce some really powerful data structures and trees and all kinds of things. Trees, we'd have 2 nodes instead of 1. We'd have a left and right. If you ever anybody talk about, and especially in C++ realm, it's still very popular to talk about L value and R value. That's left and right when we'd have a tree and we'd have a left and right value. And, when you have to move things around and change stuff, maybe you've added a node or you're removing a node. But this is a very simplistic concept that it has a lot of powerful ramifications. And there are still data structures in C# and other languages that basically underneath are creating exactly what we see here. They may be generic and you give it the data type. And it internally points. So this actually has a representation of the next pointer. But if we made this a generic and said, you're going to tell us, you're going to have to pass us the class that you want to store, and internally we'll point to a new one, if you will. We could do something similar with C. In C++, we'd use templates or something like that, although they're moving away from there, actually getting to true generics. But those concepts are still there. And this thing is driving me nuts, this screwdriver looking thing. And so remember, we're pointing to the next item and in some fashion. And here we use a reference, and here we actually technically do use a pointer. And you see that even in C, that here we have a class definition. We don't say class list item, but in C we have to say struct list item. This is old school. But we have a nice object-oriented encapsulation presentation where we use a static and we pass it the head, and it internally does the skipping as opposed to externally. And so the main program doesn't really know or care. It just knows, hey, I'd have to do this syntax. That's it. And there are other ways we can implement this. So thank you for joining me for episode 6 of the Braincast. I'm going to be getting back to these a bit more often. We're going to be looking at other things too, functional programming in Haskell and maybe F# and some other stuff as time goes on. But this is one of these things you learn very early in computer science. I learned it my first year. I don't remember. I did this in Pascal, but it's a very, very powerful concept that can be abused very easily, but it makes for some marvelous data structures and some other ideas. And we'll get on to B trees and balanced trees and all this kind of stuff. We'll look at some C code. I'll dig up some old books. We'll look at it in C# instead of references, or maybe we'll look at F# or Haskell or Scala or something. Well, I don't know. We'll see. But there you go. So there is the concept. Thank you very much. I know we didn't do any camera work on this episode, but the screen captures are really good. And I really enjoyed trying to do this coding, and live coding not so much, but I really have to think about what I'm doing. And I refactored this multiple times to get down to this type of stuff. And I will make some files and links, and we'll put it in the description below for those who are interested in the actual data files themselves. We'll do this one, we'll do the program, and we'll do this one. And we'll have links so you can download them and the like. All right. Thank you very much. Please share this video. Please let us know what types of computer science nerdery you'd like to see. What kind of programming concepts that you maybe have questions about. You're not really clear on what's going on. Let us know. And it can be even, theoretical computer science stuff. If you've got computational theory questions, you want to know what a push down automata is, you're not sure what a non-deterministic state machine is, hey, we can have some of those discussions, and we can show not only some nice diagrams, but put some of these practices into code so that you can become a better developer as well. All right. Thank you very much, and we'll see you next time. Goodbye.